Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're doing some advanced stoichiometry. I did stoichiometry, I did gas laws, I did stoichiometry, I did limit reactants in Chem 1 notes, but I didn't cover these combinations just because it can be a bit too much for first-year students. So we're going to cover it in the second year. Remembering, if you need to go back, review the stoichiometry, review the gas laws. When we talk about these, the gas law we're going to talk about is a combined gas law. In case you forget, combined gas law is P1 V1 over T1, P2 V2 over T2, combination of Charles, Boyle's, and Gay-Lussac's laws there as far as we go. All right, so let's take a look at the problem. Determine the volume of carbon dioxide gas formed if 87.45 grams of ethane C2H6 reacts with excess oxygen at 35.8 degrees Celsius and 110.8 kilopascals. Now, whenever we do this, if you start with a mass, we're going to do stoichiometry first, okay? And then we'll do the gas law after that, okay? So let's start with the reaction here. So whenever we have stoichiometry, remember the first thing we do is write the balance equation. Oxygen, a hydrocarbon, combustion reaction, carbon dioxide and water, balance it up to there because we have to multiply through, and that's our balance equation. All right, we're going to start with ethene, which is C2H6, so 87.45 grams of ethane rather, and we're going to convert that. This one in grams, we're going to go to moles, so atomic mass, carbon is 12 times 2, 24. Hydrogen 1 times 6 is 6. 6 and 24 is 30 grams. Remember, I go to whole numbers with copper and chlorine. You might have a teacher or professor that wants you to go to all the decimals. That's cool. That's just the way that I do it. All right, now we're going to work with ethene and carbon dioxide, oxygen and water. We don't worry about it at this point. The molar relationship is 2 to 4. So we put 4 moles of carbon dioxide over 2 moles of ethane. And then I want volume, so we're going to look at molar volume. Molar volume, of course, is 22.4 liters of carbon dioxide in 1 mole. Our grams of ethane cross out, my moles of ethane and my moles of carbon dioxide, leaving with liters of carbon dioxide. So answer comes out to be there, 130.6 liters of carbon dioxide. Now, we're going to do combined gas law, okay? So now what conditions are we at? Well, that's my first volume. Remember, this is at STP. 22.4 liters here is at STP. So for kilopascals and degrees Celsius, which we're going to convert to Kelvin, we're going to have 101.3 kilopascals and 273 Kelvin. Now, we're going to go to the conditions listed in the problem there. So we're going to go to 35.8 degrees Celsius, 110.8 kilopascals, and our volume is going to be unknown. We're going to solve for V2 rather. So V2 is going to be equal to P1, V1, T2 is going to come up, P2 is going to come down over T1. Put our values in. Our kilopascals cross out, our Kelvins cross out, left with liters. We take 101.3 times 130.6 times 308.8 equal, divide by 273, equal, divide by 110.8, equal. I'm going to get 135.1 liter. That's my answer. That's my first set. So if I'm giving you a mass, we're going to start with stoichiometry first. All right, now we're going to go the opposite way. Determine the mass of potassium chloride needed to decompose into 16.85 liters of oxygen at 91.7 degrees Celsius and 1.099 atmospheres. Now, in this case, I'm not giving you, it was wrong with the volume, so when giving you volume, we're going to do combined gas law first. All right, so take our P1, V1 over T1, P2, V2 over T2, and we're at, so this is the condition that we're at, so my P1 is 1.099 atmosphere, my V1 is the 16.85 liters, and my T1 over here is my 91.7 plus 273 is going to give me 364.7 Kelvin. I'm going to go to STP, so I'm going to go to 1 atmosphere and 273, solving for V2. V2 is going to be equal P1, V1, T2 over T1, P2. Put our values in. Atmospheres cross out, Kelvin cross out. We're going to get 13.86, but remember, this is at STP, and we want these conditions or we need that. The reason why we need it at STP is so we can use 22.4 as our first fraction. So let's do the reaction here. Potassium chlorate decomposes. Remember that's metallic chlorate. Metallic chlorate forms metallic chloride plus oxygen, balancing it up. All right, so we take our oxygen and we had to convert it to STP so we can use that 22.4. And then we're doing potassium chlorate and oxygen. So that's a molar relationship, 2 moles potassium chlorate over 3 moles of oxygen. And then we want mass potassium is 39, chlorine 35.5, oxygen 16 times 3, 48, 35.5 and 39 gives me 122.5. So take your calculator, take 13.86 times 2 times 122.5 equal, divide by 22.4 equal, divide by 3 equal. Remember our sig figs? We only have 4 here, so we have 4 in the answer. Answer is going to be 50.53 grams of potassium chlorate, and that's my answer. All right, let's take one more of these just to make sure that we're doing good. Find the mass of sulfur needed to produce 18.99 liters of sulfur trioxide at 90.96 degrees Celsius and 1,004 millibars when sulfur reacts with oxygen. Now remember which one we're going to do. I'm giving you volume there. So if I'm giving you volume, that means that we need to do combined gas law first. All right, so those are my conditions I'm at. And remember, standard for millibars is 1,013 and standard temperature. So solving for V2, plug the answers in, cross out the units. I get 14.12 liters of sulfur trioxide. Now we're going to produce sulfur trioxide, and it's going to be reaction of sulfur plus oxygen. So sulfur plus oxygen, sulfur trioxide, balancing it up. It's going to be 2 moles of sulfur plus 3 moles of oxygen is 2 moles of sulfur trioxide. Okay, those are 2 we're working with. We did combine gas law first so we can get into 22.4. So that's our first equation, 1 mole sulfur trioxide, 22.4 liters. We're going to use the molar relationship, sulfur trioxide to sulfur. And then the mass of sulfur is 32 for every mole. So multiply through 14.12 times 2 times 32, or we can just simply divide those through and not worry about that. Divide by 22.4, 4 sig figs. Answer is 20.17 grams. Now, not too bad, hopefully. Now, this next one is going to be incredibly easy if you can just get your mind around what's going on. Calculate the volume of sulfur trioxide formed when 15.90 grams of oxygen reacts with sulfur. Same reaction we just did. Okay? And what we're going to do is we're just going to do the molar relationship. Wait a minute, what about the combined gas law problems? Well, here's the thing. We're going to do combined gas law to start, combined gas law to end. We're going to cross each other out. If you don't believe me, go through and do the work. When we do combined gas law, we're going to take oxygen. Oxygen will be 53.64 liters. We run it through stoichiometry. We're going to get 35.76 liters. And then we take it back the other side through combined gas law again. We'll get 37.27 liters. So you see, we just make our life a lot easier. If we're going from liters to liters, we don't have to worry about combined gas law, just do the stoichiometry. And we also don't have to worry about 22.4 because they'll cross out. All right, one last problem. Okay, what is the volume of carbon monoxide that is formed when excess oxygen reacts with 18.995 grams of carbon? I'm not going to give you an easy one here. At 100.99 kilopascals and 36.99 degrees Celsius. So I want you to do this on your own. Pause it. And in case you get stuck, that's my reaction. Carbon plus oxygen, carbon dioxide. All right, pause it, work through it. Okay?
That's monoxide.
All right. Ready? Here we go. Answer there. Look through all the work. Pause it. Look at it. Answer is 40.385 liters. And that's liters of carbon. Make sure I'm right. Carbon monoxide. All right. That's it. Hopefully not too bad. Take care. God bless.